Hi, welcome back to Moose and Chemistry. Today's lesson is VSEPR Models Lesson 5. Today we're going to look at some more complex structures using the VSEPR models. We're going to start off with the compound, hang on for a second, change the color there. I thought I had the right color, but it must have changed on me. Okay, we're going to start with the compound xenon tetrabromide. Well, the first thing you notice that xenon is a noble gas. So to make this even work, we have to use an incredible amount of energy to force this issue. So let's go ahead and put this together. So when we look at this, xenon is in group 18. So it has 8 valence electrons. Bromine is in group 17, of course. Has 7 valence electrons. 3, 4, 5, 6, and 7. All right, now let's go ahead and figure out how many valence electrons we have total. So xenon is 1 times 8 valence electrons, and bromine is 4 times 7 valence electrons. This gives us a total of 28 valence electrons. We have 8 valence electrons with xenon, so this gives me a total of 36 valence electrons. So what we want to do is we want to do like the other structures we've been doing. We'll put Xe in the middle, and then we'll have Br wraparounds like this. The first thing we have to do is connect the wraparound atoms to the core. 2, 4, 6, 8. So we used 8 valence electrons. 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. Oh, so where we're going to put the other 2 electrons. Oh, well, actually the other 4 electrons. So we're going to put 2 here, 34, and then 36. So let's check our formal charges first to see if the structure is the best possible structure. So we'll do formal charge over here. We'll take the formal charge of Xe. Remember that formal charge is valence electrons minus non-bonding electrons minus bonding electron pairs, okay? So we have a total of 8 valence electrons minus non-bonding pairs. We have 4 of those because we've got 2 here and, of course, 2 there. So minus 4 sticks, so that would give me a total of 0. Which is great. That's exactly what we want. So this structure is looking pretty good so far. Now, we don't have to pick all the bromines. We can just pick one of them. It doesn't matter which one. I'm just going to pick that one, okay, for argument's sake. So what we're going to do is we're going to put together the formal charge for bromine. So remember that bromine comes in with 7 valence electrons minus 6 non-bonding valence electrons. You can see those right there. Let's go ahead and erase that real quick. Minus, of course, 1 bonding pair, which is right here. So we're going to throw that out. And that's going to give me 0, which is also good. So we know this works really, really well. The formal charge confirms. Now, let's look at this a little bit better. So what I'm going to do is I'm going to draw my structure a lot larger. So let's see here. I'm going to put Xe in the center here, Br, 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 and of course Br. Connect them up again. Put my wraparound electrons on each of the atoms. So we're getting there. Put 2 here and 2 there. I guess you could put 2 here or 2 there if you. I guess you could put 2 here if you wanted to, or 2 here if you wanted to. I don't think it really matters. So anyway, let's get back to what we're doing. So what we want to know is what is this structure's VSEPR model? So our Xe is our core, so we get an A there. We have an X1, X2, X3, X4. This is going to be E1, and this is going to be E2. So this would give me AX4E2. Now, AX4E2 is going to be a square planar, and you don't really see a lot of these, and it has a 90-degree angle. Now, what about the hybridized orbitals for each of these atoms? Well, let's look at bromine first. Okay, bromine, remember that hybridized orbitals use only sigma bonds, which represent the dashes, and unshared pair lone electrons. So these are lone electron pairs. So when we look at bromine, we have 1, 2, 3 lone electrons pairs, and we have one shared pair, one sigma bond. Remember, that's called a sigma bond. So for bromine, our orbitized, we have 4 things. So we have 1s and 3p. That's our hybridized orbital for bromine. Now let me go ahead and erase some of this because it's getting a little bit crowded in here. So we're going to get rid of some of this stuff here. Kind of clear it out a bit. And we're going to look at the hybridized orbital now for Xe. So Xe, one moment, Xe, okay, has 1 unshared pair, 2 unshared pair, and then it has 1, 2, 3, 4 shared sigma bonds. So this gives me a total of 6. So S holds 1, P holds 3, so that would give me 4, and then the last 2 would be D, so it would be sp3d2. Okay, so that's really good on that one. Let's look at another model. So let me go ahead and erase all our drawings here. And we got that. And so let's look at CS2. Now, CS2 is carbon disulfide. So carbon has 4 valence electrons because it's in group 14. Sulfur is in group 16 and has 6 valence electrons. So let's figure out our total number of valence electrons. So we go carbon is 1 times 4 valence electrons. Sulfur is 2 times 6 valence electrons. This gives me 12 valence electrons and 4 valence electrons, which are 16 valence electrons. So that's good so far. So now whatever structure we draw has to use up 16 valence electrons. So let's go ahead and draw the structure, and let's go and make it over here. So carbon goes in the center, put S to the right and S to the left. So remember, we got to connect carbon first. 2, 4. Now we have to finish this. 6, 8, 10, 12, 14, 16. Okay, there's a problem with this structure. We don't have to do the formal charges to know there's a problem. Carbon here is in group 2, so it has to have an octet. I mean, it's in period 2. So it needs an octet. So to get an octet for carbon, we're going to have to take 2 electrons off of here and off of here. And then we're going to place those electrons here and here. But when we do that, those other electrons don't want to be nearby. So let me erase these for a moment. I'm going to reposition them. And that's going to give me 2 electrons like this. And see, everything is spread out nice and neatly. Okay, let's check the formal charge to see if this is a better structure after all. Remember, the formal charge is valence electrons minus non-bonding electrons minus bonding electron pairs. So carbon comes in with 4 valence electrons. There are no non-bonding electrons in that. And there are 4 bonding pairs. So that gives us 0. That's great. Let's check out the formal charge for one of the sulfurs. We don't have to do both of them because they both look the same. So sulfur has 6 valence electrons coming in minus 4 electrons, because you got 2 here and 2 here, that have not been used. And that has also 2 bonds right here. This gives me a total of 0 also. So this is the best possible charge. Now let's look at the VSEPR model. So the core is A, this is X, this is X. We don't have any unshared pair in the core, so it's all done. So we call this AX2, which is a linear structure, and it has bond angles of 180 degrees. Now let's check for the hybridized atoms, okay? So carbon has a sigma bond. Has 2 of them, as a matter of fact. So the first sigma, well, it has actually 2 pi bonds. We have a sigma bond, and that's the first one, and we have a pi bond on the second one. So pi bonds don't count in our hybridized orbitals. So let's go ahead and clear all this. Erase this here real quickly. And so we've got that all erased again. I wish I had a bigger eraser. It'd be kind of nice, but we got to go with what we got. So carbon's hybridized orbital has 1 sigma bond, 2 sigma bonds. So carbon would equal sp, 1 for s, 1 for p. Sulfur, on the other hand, will have something quite different. When we look at sulfur, we have a lone pair, and 1 sigma bond. So that gives me sp2. And that's that structure. Okay, let's look at another structure real quickly. This will actually be our longest video so far, and I don't like to make them too long. So we'll clear this out, and we're going to look at ClF5. Now this is a challenge in itself. So ClS5 is going to be quite a bit different. Get rid of all that there. There we go. And ClF5. Well, chlorine is in group 17 and has 7 valence electrons. Fluorine is also in group 17 and has 7 valence electrons. Now, you got to think to yourself, well, they both have 7 valence electrons. But remember that chlorine is the most electronegative element out there. So, not chlorine, but fluorine. So we're going to use chlorine as our core. So we got 1 chlorine at 7 valence electrons, and we have 5 fluorines at also 7 valence electrons. This gives me 35 valence electrons. Wow. I just got a phone call. As you can tell, my ringtone is Tom Petty. Anyway, so let's go on to, here we get total 42 valence electrons. Now we're going to set up our Cl. And what we're going to do is I'm going to put 5 F's around here. So I'm going to kind of put an F here, an F there, an F there, an F there, and an F there. So now we're going to count out 48 valence electrons. That doesn't look like a good F. Let's make that better. There we go. So it's 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40. Now we have 2 valence electrons left, so they're going to go back into the core atom. And we're going to definitely violate the octet of rule with chlorine. So anyway, let's check the formal charge to make sure this is good. So the formal charge of chlorine, and now remember that it's valence electrons minus non-bonding electrons minus bonding electron pairs, okay? So with chlorine comes in 7 valence electrons. Non-bonding, we have 2, and we have 5 bonding pairs. So we get 0. That looks really, really good. Let's do the formal charge for fluorine. Okay, fluorine comes in, of course, with 7 valence electrons, minus 6 non-bonding electrons, minus 1 bonding pair, and that gives me 0 also. So I'm liking this a lot. The formal charge is looking good here. So now let's look at the structure. Okay, the chlorine is our A, so we have X, 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 and this pair right here is going to be called E1. So this is AX5E. Now an AX5E is a square pyramid. So, and again, these are uncommon too. Let's see, we need to do one more thing. Oh, yes, the hybridized. And the angles on this are 90 degrees. Okay, now, so let's kind of undo some of the writing I just did there. Whoops, I didn't mean to get rid of the 90 degrees. I guess I'll just have to use the eraser. So I'm going to erase this here, so it doesn't get too, clogged up, and you can't I can't see what's going on. So I'll have to put those dots back in there, of course. So just give me a moment. Get rid of that A there, and of course we need the 2 dots back. And there we go, we're back in business. Okay, so now what we're going to do is we're going to do the hybridized orbitals. So chlorine, Cl. Now remember that sigma bonds, which are dashes, and lone pairs are what we use to determine the hybrid orbitals. Remember that S has 1. P, slightly higher orbital, has 3. D, slightly higher orbital, 1, 2, 3, 4, 5. And of course, F, much higher orbital, has 7 of these suborbits. So I'm going to clear those out real quickly. Looks like I got to do some erasing. Okay, so now we're going to count the chlorine here. We got 1, 2, 3, 4, 5 sigma bonds and 1 lone pair. So that gives us a total of 6. So 5 sigma bonds and 1 lone pair. So S takes 1 of them, P takes 3. So that's 4, and then, of course, we want 5, so it would be sp3d. Two. Yes. sp3d2, I believe. All right, so because that gives us 6 total. Right, it sure does. So now let's look at the fluorine hybridized. So there are 1, 2, 3, 4. So we're going to use up 4. It'd be S, P, 3. And that's it. You guys have an awesome day, and I look forward to seeing our next videos on Moose and Chemistry.